All right, welcome back, everybody. Welcome back. This is Modern Mathematical Methods for STEM Majors, and I am Dr. Richardson. I'm really happy and excited to introduce you all to Chapter 6, which is all about trigonometry. Okay, trigonometry is just one of the most fundamental fields in mathematics, one of the most fundamental subjects. It's incredibly beautiful, and it's utilized all over STEM, math, science, you name it. Okay, let me pull up the slides. We'll get started. And we'll take a look at an overview for the chapter before we take a look at the overview for the section. All right. Okay. So, like I'd said, this is like the trigonometry chapter. So, all about trigonometry. The first section, the one we're going to do today, is all about circles. Good news is we've already studied circles pretty significantly. So, a lot of the stuff you see in this section is going to be a little bit of review from what we've seen in the past. The next section, 6.2, is all about angles, angle measurements, getting used to angles, standard angles, uh, angles to memorize, angles to recognize, etc. Section 6.3 is where we're going to introduce the trigonometric functions themselves. And then section 6.4 is where we'll talk about right triangle trigonometry and the law of cosines. Right triangle trigonometry has to do with a SOHCAHTOA. If you've heard that mnemonic device before, that'll be 6.4. Then we'll talk about the graphs of the trigonometric functions. And then section 6.6 is actually all about graphing transformations of those functions. This is a skill that you're going to need heavily in the calculus sequence and just beyond as well, knowing what these graphs look like when they're shifted, stretched, all sorts of things. So there's a whole section on that, all right? Then we're going to talk about inverse trigonometric functions. Good news is it's the same idea we talked about back in chapter 2 when we studied inverse functions in general. It's just now it's applied to trigonometric functions. Then we're going to do a section that includes some trigonometric identities, not all of them, but some of them, because there are literally hundreds of them. Okay. Then we'll finish off the chapter and the course with solving some trigonometric equations. This is a good skill to have. You're going to need it a lot in calculus, so it's a good way to kind of end the course. There is a supplementary chapter after chapter 6 that I leave to you all to watch on your own free time during the break to prep for some of your other courses. All right. Okay, so let's talk about circles for a minute. Let's look at this section. We're going to get the geometric definition of a circle. Then we're going to review the Pythagorean theorem and just see how it relates to the equation of a circle. Then we're going to talk about the standard form of the equation of a circle, which you actually derived on your own in an activity. So it should look very familiar. Then we'll talk about the unit circle, which we've also seen in the past. Then we'll talk about something new that we haven't seen yet, the general form of the equation of a circle. And then we'll finish off by reviewing and exploring the semicircle functions. We did see those in the past. A couple of those are the functions of some important graphs that you wanted to memorize back in chapter 2, but we're going to generalize them a little bit. All right. So let's start with the definition. So what is a circle? A circle is a set of points in the plane that are a fixed distance r from another fixed point h comma k. And that's it. So geometrically, that's what a circle is. So a set of points that are a fixed distance from another fixed point. So you can kind of imagine, here is a fixed point. We call it h comma k. And then there is another fixed number, what we call r, like so. And a circle is the set of all points that are exactly r away from h comma k. So pretend this is a really nice circle. Ah, and yikes. Pretend this is at the center of that circle. There you go. That's not too bad. Okay, so r is what we call the radius of the circle, and the point h comma k is what we call the center of the circle. All right, so now let's recall the Pythagorean theorem. We talked about this very early on in the course. We're going to see it show up a lot in trigonometry. So given any right triangle with legs of length A and B and a hypotenuse of length C, this equality holds. A squared plus B squared equals C squared. And here's a picture of that right triangle. So now what we're going to do is we're going to see how this will help us make sense of the formula for a circle, the equation of a circle, my bad. So if we place the lower vertex of that triangle at the origin, then we can see that the length c, this hypotenuse of length c, forms the radius of a circle that is centered at the origin. So here's that lower corner, and c is going to end up being the radius of a circle, okay? That's the basic idea. And then this point here, this is the point A comma B, now that we've placed things on the coordinate plane, right? This is A and this is B. So this point is the point A comma B. All right. Now we're just going to relabel things. It's all we're going to do. So if we relabel things and we apply the Pythagorean theorem again, we get the standard equation of a circle of radius r centered at the origin, this right here, that right there. And we've seen this before. We saw this back in chapter 2, but this is just showing you exactly where that formula is coming from via the Pythagorean theorem. And all I did was relabel it. I relabeled this as x and relabeled that as y. There you go. That's it. That's it. Okay. So what is the standard form of the equation of a circle centered at the point h comma k? Well, this is actually a formula that you derived back in chapter 2. I think it might have even been section 2.2 or 2.3, but it was this equation that we derived during an activity, right? So in essence, what's happening here is this is describing a circle that was centered at the origin, but then it was translated along the vector h comma k to the point h comma k. So it's basically moving the center of the circle and therefore the circle itself to wherever that new point is, wherever that new center is going to be. All right, let's do an example here. Let's do an example. I want you to write the standard form of the equation of a circle with radius 1.75, decimals are allowed, and center -2 comma 1. This is one I do want you to try on your own. It's a good way to get those juices flowing early. So think about it for a second. What could that form look like? And then, as always, say something out loud. Remember, even better if you're doing this with a peer, watching together, talk to each other right now. If not, talk to your dog, to your cat, talk to yourself. It's okay to talk to yourself. Don't feel weird. Just give your brain that feedback so it can make sense of things. All right, and now work it out on your own. You're just writing out the standard equation of the circle with this radius and that center. And we'll do it together in a second. All right, here we go. So we're given the radius, we're given the center. It's pretty quick and easy to write out the formula. H is -2, 1 is k. So h becomes -2 and k becomes 1. And the radius is 1.75. Now we can simplify a couple things and we get this as the equation of that circle. And then here's a picture of the circle just to kind of sketch it out. The center is at -2 comma 1. The radius is 1.75. So we just move out 1.75 units from this point. So for example, if we moved vertically, directly vertically from that point, we would be adding 1.75 to 1 to get 2.75. Down here, we would be subtracting 1.75 from 1 to get, what is that, -0.75. Maybe I'll put another point right here. Yeah, this is the point -2, -0.75, for example. And that's how you can plot at least 4 points on the circle. You just kind of move up, down, left, right, and that's how you can plot the circle. All right. Another way of understanding this is we basically started with a circle of radius 1.75 that was centered at the origin, but then we shifted that circle along the vector -2, 1. That's -2 units to the or 2 units to the left, and then 1 unit upward to go right along that vector. And that's it. And again, that's why the standard form of a circle is nice because you can see the center, you can see the radius, you can read it off directly. Okay, now let's review the unit circle. Okay, so the unit circle is a circle of radius 1 centered at the origin. All right, so this guy right here is the foundation for all of trigonometry. The equation of this circle is x squared plus y squared equals 1. You definitely need to have this memorized. And this is the picture that you want to have just burned into your memory because we are going to see it a lot over the next several sections. Okay. So the unit circle, this is what I mean. Okay. Now let's talk about the general form of the equation of a circle. So another form, oh yeah, is the general form. Um, excuse me. In example one, we had this standard form of that circle. So if we want to get the general form of a circle, all we do is expand everything and move everything to one side. That's all we got to do. So multiply everything out and move everything to one side. So here I expanded x plus 2 squared. I expanded y minus 1 squared. I expanded 1.75 squared. There it is. And then I moved everything to one side. And then I grouped the terms a little bit. So what I did was I put all the square terms next to each other. And then I put all the linear terms next to each other. And then I merged all of the constant terms. That's what I'm going to do with 4 plus 1 minus 3.0625 to get that right there. And this is the general form of the equation of that circle. That's it right there. So going from standard to general is really easy. Expand everything, move everything to one side, and then group, I'll say group like terms, I guess. The squares, the linears, the constants, and that's it. Now, more generally, pun intended, the general form of a circle is this: x squared plus y squared plus ax plus by plus c equals 0, where a, b, and c are real numbers. So this is the general form written in this order and in this structure. So some details about it. The general form can be helpful for analysis because the square terms are grouped and the linear terms are grouped, and they're kind of like separated out, pairwise. It is not so helpful when you're trying to graph the circle by hand. And we saw this same phenomenon earlier in the course when we were talking about, oh geez, all sorts of things, standard forms of polynomials, standard form of a line, all that kind of stuff, right? So it can be helpful for analysis, but the downside to this particular structure is we can't see the center and we can't see the radius. That information is baked into all of these values here. One thing we can see is that this is definitely describing a circle because of this expression here, the x squared plus y squared. That is necessary for this to describe a circle, all right? The remaining terms that you see here, those are encapsulating any shifts or any radius changes or radiuses that have been applied. So yeah, you can't really see that because it's all baked in right here. Now, what do we want to do, or how do we go the other way? We saw how to go from standard to general. How do you go from general to standard? Well, we're going to use that good old technique that we've seen before, completing the square. And we're going to complete the square 2 times. All right, we're going to complete the square twice. Here we go. Let's consider this circle for a minute. And actually, Hmm. Hmm. I think I will have you try to do this one on your own first. But let me give you some tips first. So this is definitely the equation of a circle because of this x squared plus y squared expression right there. Now, the downside is we can't see the center and we can't see the radius the way that this is written, and we're being asked to graph the circle or sketch the graph of the circle. So we're going to have to complete the square. And I do want you to try this on your own, so listen carefully. What I want you to do is I want you to put the x terms together and the y terms together, and then I want you to complete the square on those resulting pairs, okay? So think about it for a minute. And now speak something out loud about what you can do to start the process. Maybe just kind of repeat what I said. All right, now try to work it out on your own. Remember, you will be completing the square twice. You're going to do that 2 times on the x terms and then the y terms. And then merge all the constant terms together when you're done, and then you will have the standard form, and we'll do it together after that. All right. Here we go. So like I had mentioned, the first thing we're going to do is group the x terms and the y terms together, like so. And then these are what we're going to complete the square on. We're going to complete the square on each one of them individually, just like so. So remember, when you complete the square, you're just adding 0 in a clever way. So we're going to add 0 by adding 9 and taking it away here. That gives us a perfect square trinomial right there. Here we're going to add 4 and take it away. And that gives us this perfect square trinomial. And now what we're left with is two perfect squares, and then we have a bunch of constant terms right here. We're going to mush all those together, mush all those constants together, and then throw the final result to the other side, and we get this right here. So this is now the standard equation of that circle, but now that it's in this form, we can immediately read off the center and the radius and then graph it, right? So just looking at this form, we can see that the center is going to be 3, -2, and the radius is going to be the square root of 1, which is 1 in this case. Now we can graph it. Center is 3, -2, and the radius is 1. And that's it. Not too bad, right? So we've gotten a lot of practice with completing the square, so hopefully this isn't too bad. If it is a little bit tricky, don't worry, because we're going to do it in activity anyway. Okay, another example. I want you to try to find the general form of a circle whose center is 2, -5, and whose graph contains the point 3, -8. Okay, ponder this one for a minute. Okay, now say something out loud. Maybe even just reread the question out loud. That can always help, right? And now work it out on your own. You're going for the general form of that circle given that information. Maybe a hint, start with the standard form. That's a good way to start. Start with the standard form and then convert it into the general form. Okay, here we go. All right, so first of all, we already know the center. Boom. So we've got the center, uh, but we don't know the radius. That's what's missing. If we had the center and the radius, we would be done, right? We could write it, or not done. We could write it in standard form and then quickly get the general form. But all we know is the center, and we know another point on that circle. But remember, a circle is the set of all points that are equidistant from the center. So we're given a point on the circle. So all we need to do is compute the distance between those 2 points, and that distance will be the radius of the circle. So that's what we're going to do. We're going to use the distance formula, the good old distance formula, the Pythagorean theorem in disguised, and we're going to find the radius. Here we go. 2 minus 3 squared, -5 minus -8 squared. Add those two results, and then take the square root, and that will give us the radius, the distance between those 2 points. Now, 2 minus 3 is 1. -5 minus -8 is -5 plus 8, which is 3. And 3 squared is 9. And then 1 plus 9 is 10. So our radius in this case is the square root of 10. Now we've got everything we need to get to the general form. We've got the center, we've got the radius. Let's put it in standard form first. Boom. Instant, right? Here's the center. And then this is square root of 10 squared. And that's the form. Now, expand everything. I'll skip that step because it's pretty straightforward. Just multiply this out. You expanding the binomial. Same with this. It's also a perfect square trinomial, so you should know that form. And then mush all the constant terms together and move everything to one side. And then group the squares, the linears, and the constants. And that's about it. Okay. Now, the last thing we're going to talk about is the semicircle functions. So we're going to start again with the standard form of a circle. And you might remember, we've talked about it a few times, that the equation of a circle does not represent a function of x nor a function of y. But if you solve for those variables, you will get two functions for, well, you'll get functions for the top, the bottom, the left, and the right semicircles. A couple of these are formulas that you were supposed to memorize earlier on in the course. back when we were looking at those important graphs to memorize. Now we're just generalizing it a little bit because our circle may not be centered at the origin anymore. But we're going to do the math right now and take a look at some pictures to make sense of it. So let's start by solving for y. We're going to take this equation and solve it for y. And when we do that, we are going to get two formulas, one for the top semicircle and one for the bottom semicircle. So here we go. Just follow your nose, move everything away from y, and remember to add a plus minus whenever you take a square root. So we get this. We're going to square root both sides. There's that plus minus. And then we're just going to add k to both sides to get this. Now, this is actually two equations mushed into a single equation. But when we take the positive sign here, we get the equation for the top semicircle. And when we take the negative sign here, we get the equation for the bottom semicircle. Now let's look at a picture, okay? Let's look at a picture. This one is actually precise too, but here's the top semicircle. Here's the bottom semicircle. And here I used that same circle we looked at before, the one that's centered at 2, 1, and has a radius of 1.75. And again, as it's written down here, that's not going to describe a function of x nor a function of y. But when you solve for y, you get the formula, the function for the top and the bottom. So this is what the top semicircle looks like, and this is the function for it, right? X and y. So you might notice that everything's being shifted up by 1 because the center has been moved. X is also being shifted 2 units to the right because the center has been moved. And then this is the radius squared. And so that's what this is right here. Now for the bottom, it's the same idea, except now this is going to be reflected across this line right here. So we're still shifting up by 1 and to the right by 2, but now we're going to take the bottom half of that semicircle, and that's why we have that negative sign right there. Not too bad, right? That's it. Might look a little bit messy, but it's still going to have that structure of square root of r squared minus stuff, except now it's also shifted. Okay, now instead, if we solve those equations for x, we get formulas for the left and the right semicircles. So same process, the calculation is almost identical, except now we're solving for x. We get this, take the square root of both sides, include the plus minus, add h to both sides, and we get this. So this is going to split up into the left semicircle and the right semicircle. And again, if this is negative, it's going to be on the left. Wait, is that right? Is that right? Is the left the right? I'll just say, if this is negative, we're getting the left. And if this is positive, we're getting the right. I'll just say it like that. There we go. And then using that same circle as an example, here it is. This is that circle, x minus 2 squared plus y minus 1 squared with a radius of 1.75. And now we've got the formula for the left and a formula for the right. And that's about it, okay? Just shifted. Same idea, but just shifted. Now, the ones that you have seen before that you needed to have memorized are these ones. So these are the ones when the circle is centered at the origin 0, 0. And the reason that I really, really want you to memorize these particular formulas is because you will see them show up so many times in Calc 1 and Calc 2 and Calc 3. Anytime you see a structure like that, you should be thinking circles, semicircles, the top, the bottom, it's circular. Which one is it? Well, if it's positive, it's going to be the top semicircle. If it's negative, it's going to be the bottom semicircle, right? When you have y equals some function of x, all right? That's the basic idea. Here it is. This one, yeah, just a general radius. So this equation here is giving you the function of this top semicircle. This equation here is giving you the function for this bottom semicircle. And that's it. So make sure you can recognize these structures and map them to these pictures in your mind, okay? Make sure they match up in your mind. Now we can do the same thing for the left and right semicircles. So again, you just solve for x instead. This is going to be the left semicircle. This is going to be the right semicircle. Here, y is our input and x is our output. And the pictures are going to look like this. There we go. Okay. So again, the left one, because this is negative, the right one, because this is positive. And again, you'll see these types of things a lot in calculus and beyond. So you want to make sure that you're comfortable with them, that you can recognize them, and that's it. That's it. So on that note, let's play. All right, let's play. This is a bit of a short section, mainly because we have studied this stuff before, but it is an important section. You got to be really, really comfortable with circles if we're going to talk about trigonometry. Trigonometry involves circles. It also involves right triangles. It comes together in these really beautiful ways. I'm super excited to get into it. Okay. On that note, I will say bye for this time. Thank you again for watching and I will see you next time when we talk about angles. Have a good one, everybody.